Hello there, and welcome. Tonight, we'll drift into something vast, not just in size, but in wonder. The universe is not what it seems. It's colder than fire, louder than silence, older than time, and filled with things that defy explanation. There are stars that pulse like hearts, planets made of diamond, and voids so empty they swallow light itself. The deeper we look, the more we realize, reality doesn't just stretch our imagination, it breaks it. These are not just facts. They're riddles, paradoxes, and whispers from a cosmos that has never stopped surprising us. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or press the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. In the silence of space, size is not measured in miles or kilometers, but in something stranger light that takes years to arrive, shadows cast by ancient stars, distances so immense that numbers become symbols rather than meaning. The universe is not just big, it is bigger than your ability to imagine, bigger than your mind can stretch before it folds in on itself, bigger than anything we've ever lived long enough to understand. Consider this. The moon, so close it pulls at our oceans, is about 384,000 kilometers away. Light from it takes just over a second to reach your eyes. A second. The sun is 150 million kilometers farther, and light from it takes 8 minutes to arrive. That's already strange, seeing the sun not as it is, but as it was minutes ago. But let that stretch a little farther. The next closest star is Proxima Centauri. If the sun is a short stroll away in cosmic terms, Proxima is a marathon. Light from there takes over 4 years to arrive. That's 4 years of time embedded in every photon. When you look at it, you're seeing the past. Now, look farther. The center of our galaxy, a bright, dense swirl of stars called Sagittarius A*, is about 26,000 light-years away, which means the light we see now from it left when woolly mammoths still walked the Earth. Andromeda, our galactic neighbor, is 2.5 million light-years away. It's visible with the naked eye on a dark night, a small blur barely whispering across your vision. But that blur is a galaxy of 1 trillion stars, and the light you're seeing began its journey before Homo sapiens even existed. You are not seeing it as it is, but as it was before we were here to witness anything at all. Still, we're only talking about nearby objects in cosmic terms. The observable universe stretches 93 billion light-years across. That number seems impossible, because the universe is only 13.8 billion years old. But space itself is expanding, faster than the light crossing it. So galaxies that emitted their light billions of years ago are now farther away than the time it took their light to reach us. We're seeing them as they once were, while they now sit much farther, unreachable, perhaps forever. What we call the observable universe is not a limit of existence, only a limit of what light has had time to show us. Imagine shrinking Earth down to the size of a grain of sand. At that scale, the sun would be about the size of a tennis ball, 8 meters away. Proxima Centauri would be another tennis ball over 2,000 kilometers away. The Milky Way, a disk of stars stretching across most of a continent. And that's just one galaxy. There are perhaps 2 trillion galaxies in the observable universe. Many are larger than ours. Many are filled with stars older than ours. Some are colliding. Some are disappearing behind the veil of cosmic inflation, falling forever beyond our view. Every speck of night sky, even the blackest patch, holds thousands of unseen galaxies. We are floating inside a volume so massive that our solar system is just an eddy inside an eddy inside an eddy. There are more stars in the universe than grains of sand on all the beaches of Earth. And yet, that comparison doesn't do it justice, because those stars, like the sun, may host planets, and those planets may host moons, and some of them may orbit not one sun, but 2 or 3. Some are frozen, some are burning, some are drifting alone between galaxies, not bound to anything but gravity and silence. And still, this sea of objects is just the visible part. Even now, there may be regions of the universe so distant that light from them will never reach us, not because it hasn't had time, but because space is stretching too fast for the light to ever arrive. That's the part that breaks our mental scaffolding. Space doesn't just hold objects, it changes. It warps, expands, and accelerates. The more you look, the more you understand that this isn't an empty stage with stars pinned into it. Space itself is part of the story. The distances are not fixed, they breathe. Time, too, gets tangled in this vastness. Because we can only see light that has reached us, we are always looking backward. There is no such thing as now across the universe. Now is a local phenomenon, meaningless over intergalactic space. Two stars on opposite sides of the cosmos cannot agree on what now is. Light from distant galaxies shows us their youth, while they may have long since grown, changed, or vanished. Even if you could travel faster than light, you'd never be able to see the universe in real time. You'd only skip farther into past snapshots, older frames in a movie still playing somewhere out of reach. And, perhaps the strangest part of all is that this entire cosmos, the unfathomable size, the ancient light, the frozen voids and flickering galaxies, may be only one universe among many. The concept of a multiverse isn't science fiction anymore. It's a mathematical implication of some theories. There may be other universes with different laws of physics, different constants, different beginnings. You could line them up endlessly and still not reach the edge. But if that's true, then the largest thing we can imagine is only a fragment. And our observable universe, already too big to comprehend, might just be a bubble in a foaming sea of realities, each one expanding, shifting, and forgetting the others ever existed. In the face of all this billions of galaxies, each with billions of stars, scattered across a growing fabric of space, we find ourselves sitting on a pale planet orbiting a yellow sun, a tiny, local event in a cosmic ocean. And yet, from this small place, we've built instruments that can detect echoes of the Big Bang. We've launched machines that left the solar system. We've mapped stars, weighed galaxies, and traced light that began its journey before our species had learned to speak. But knowing the facts doesn't change the scale. Our minds evolved to see trees, rivers, and predators, not neutron stars and gravitational lensing. We live in a universe that can't be pictured, only glimpsed. It doesn't fit in your imagination. It doesn't care whether it can be visualized. And still, it contains you. You, a pattern of atoms that once lived inside stars. A brief awareness, looking out into a silence too wide to hold. The universe is not big. It is beyond big. It is unknowably, quietly, immeasurably more than we can ever hold in thought. And still, we try. When you look up at the night sky, you're not seeing the universe as it is. You're seeing it as it was. Every star, every shimmering point of light is a message from the past ancient light, traveling vast distances, arriving just now to brush against your eyes. Light doesn't blink into existence across space. It moves, slowly. Even when it's moving as fast as anything can, it takes time. And because of that, the sky is a record, not a view, a memory. The light from the moon is barely delayed. It takes a little over a second to reach you, bouncing off a dusty surface only 384,000 kilometers away. When you look at it, You're seeing the moon as it was one heartbeat ago. That feels immediate, familiar. The sun's light is older, about 8 minutes old, which means every sunrise is a replay. Every ray that warms your skin began its journey while you were still tying your shoes or sipping your coffee. If the sun were to disappear this instant, completely vanish, you wouldn't know it until 8 minutes had passed. But that's still the shallow end of time. The stars you see in the night sky are older stories. The bright, twinkling one near the horizon might be Sirius. Its light left around 9 years ago. Vega's light took 25 years. Deneb's, more than 2,500. These are not snapshots. They are echoes. A shimmering parade of pasts stretched across a single present moment. Your present. Andromeda, that faint, blurry smudge, high in the dark, lies 2.5 million light-years away, which means the photons now hitting your retina began their journey before humans had ever drawn on a cave wall or shaped fire with their own hands. We were not yet what we are, and yet the light waited, carried no urgency, just direction. This isn't just an abstract idea. It's the nature of vision itself. To see is to receive light. And when distance becomes cosmic, so does time. Galaxies millions, even billions of light years away, are visible only because they flung out their light long ago. We don't see what's happening in those galaxies now. We see what happened ages past, when the Earth was still a blank page. The farther you look, the older the light becomes. It's like peeling back layers of time, each deeper than the last. If you point a powerful telescope into the blackness and let it gather for hours, even days, you begin to see what are called deep field images. And in them, the darkness is filled with light from galaxies so faint and distant, their glow has been traveling toward us for over 13 billion years. That's nearly the age of the universe itself. We're not just looking at galaxies. We're looking at baby's infant galaxies just after the Big Bang, burning with wild, chaotic energy, shaping stars in ways our modern universe has long forgotten. Some of the earliest starlight we've seen was cast when the cosmos was only a few 100 million years old, just a sliver of its current age. Light that left when the first atoms had only just begun to come together, and when the night sky still shimmered with leftover heat from creation. And even now, we can see that afterglow. It's called the cosmic microwave background, and it isn't made of stars. It's the faint whisper of radiation left over from the Big Bang itself, a kind of fossil light. It doesn't arrive in beams or bursts. It's everywhere, in every direction. A uniform glow from a time before stars, before galaxies, before structure. This light has been traveling for nearly 13.8 billion years. It has stretched and cooled across time, moving from blinding energy to a chill microwave hum. The longest journey light can take, and it's still arriving, right now, touching your world invisibly. This idea that light is a traveler and we are its final moment is not just poetic, it's physical, it's measurable, and it means that there is no such thing as seeing something now in space. There is no universal now, no synchronized moment, only a cascade of old lights, layered and arriving together in your present. That galaxy you study, it may not even exist anymore. It may have died in silence millions of years ago, but we wouldn't know. Its light hasn't told us yet. We live in a delayed universe, a place where truth and time never quite overlap. And it's not just light from distant stars that follows this rule. Even on Earth, light has a speed. Your reflection in a mirror is already a fraction of a nanosecond old. Every view you've ever seen is slightly out of sync. But the scale is so small, so close to instant, that your brain doesn't notice. In space, that delay becomes profound. It means we live in a hall of mirrors, each one angled toward an earlier version of reality. And so, when we say we're exploring space, we're also excavating time. Astronomy becomes a kind of time travel, not into the future, but into deeper and deeper memory. Telescopes become shovels, peeling back eons. We don't watch the universe change. We piece together its past. This also means that every step forward is a step backward. The more powerful our instruments become, the farther we see, but also the older. We trade resolution for age, clarity for time. We can see ancient galaxies, but never as they are, only as they were, painted in the light that finally, just now, arrived. And in all of this, we are participants, not just observers, because light doesn't just travel outward, it also comes in. The light bouncing off your skin is traveling too, escaping Earth, carrying the shape of you into the universe, faint, fragile, but real. Every moment of your life has cast photons outward that will continue on forever, touching distant particles, long after you're gone. So when you look up and see the stars, know this. You are not seeing the present. You are swimming in time. You are surrounded by the past, and the light that reaches you cold, distant, quiet, has waited across the ages to be seen, and tonight it found you. When we look into the night sky, it feels full. Stars hang in clusters. The Milky Way spills across the EMO, darkness like a river of light, and galaxies glow faintly from millions of light years away. But this brilliance is an illusion. What we can see, what emits light, reflects it, or glows in any wavelength, is only a sliver of what's actually there. Most of the universe is invisible, not just hidden behind dust or too faint to detect, but truly, fundamentally unseen. And it is this unseen substance that shapes almost everything. For centuries, we thought what we saw was what there was. Planets, stars, gas, dust, all made of atoms, the basic ingredients of matter. But as our instruments grew sharper, as we measured motion more precisely and mapped the shapes of galaxies, something didn't add up. Stars at the edges of galaxies were moving too fast. They should have been flung outward, like rocks from a slingshot. But they stayed in orbit, held by something we couldn't see. The math was undeniable. Galaxies weren't just made of stars. They were surrounded by vast halos of invisible mass, something with gravity, but no light, something that didn't glow, didn't absorb, didn't interact with radiation in any detectable way. It simply pulled. We called it dark matter, not because it's dark like a shadow, but because it's missing from view, an absence in the light, a placeholder name for something we don't yet understand. Dark matter doesn't clump like normal matter. It doesn't form planets or suns. It passes through us, and through itself, like ghosts in a dance. But it weighs everything down. It holds galaxies together. It bends the path of light. It makes the cosmos behave the way it does. If you could see dark matter, the universe would look completely different. Galaxies would wear halos like crowns, great spherical clouds of mass extending far beyond their visible edges. Filaments of invisible substance would stretch between them, weaving a web across space, linking clusters into a kind of cosmic scaffolding. The stars would be the decoration, the bright frosting on a cake made almost entirely of something we cannot touch. And dark matter isn't rare. It outweighs all the stars, planets, gas, and dust in the universe by more than 5 to 1. If you gathered all the luminous matter together, all the brilliant things we've ever seen, it would still only be a tiny fraction of the total. Most of what exists does not shine. But that's only part of the mystery, because in the late 1990 seconds, something even stranger appeared. Astronomers studying distant supernova noticed they were dimmer than expected, not because they were farther away, but because the universe was expanding faster than predicted, and not just faster than expected, faster over time. For billions of years, gravity had been slowing the expansion of space. Then suddenly, it wasn't. It was speeding up. To explain this, scientists added another unknown: dark energy. If dark matter holds things together, dark energy pushes them apart. It's not a force like gravity or electromagnetism. It's more like pressure built into the fabric of space itself. As the universe expands, dark energy doesn't thin out. It stays constant, which means the more space there is, the more dark energy there is, and the faster everything accelerates. It's a runaway effect, a quiet explosion with no center, no edge, and no sound. And dark energy is even more dominant than dark matter. If you broke the universe down by ingredients, ordinary matter, everything we've ever touched or seen, would make up less than 5%. Dark matter would be about 27%. The rest, nearly 70%, would be dark energy, the force that no one expected, the energy of empty space. Together, these two mysteries, dark matter and dark energy, define the structure, behavior, and fate of the cosmos. And yet, we don't know what either of them is. We only know what they do. We know how to measure their presence by their effects. We see galaxies spin too fast and know something is holding them together. We see supernova fade too soon and know something is stretching the space between us. They are not just gaps in understanding. They are the dominant realities of the universe. We are made of the rare stuff. We are the exception. And yet we build our entire picture of the cosmos on what we can't see. There are experiments underway to find dark matter directly. Deep underground detectors wait in silence, hoping to catch a passing particle, a flicker, a nudge, the softest whisper of interaction. Some scientists search with giant particle colliders, smashing atoms together at near light speed, looking for missing energy in the debris. Others study the sky, mapping the gravitational lensing of distant galaxies, tracing how light bends through unseen mass. We are chasing a ghost we believe in because it leaves footprints, even if it never shows its face. Dark energy is harder. It doesn't clump. It doesn't flow. It may not even be made of particles at all. It may be a property of space itself, a feature of the void. Some theories suggest it changes over time. Others suggest it may someday overwhelm even gravity, tearing galaxies apart and unraveling atoms. A slow disintegration, written into the bones of reality. For now, these are only questions, but they shape everything. Galaxies are born and held together by dark matter. The cosmic web that stretches across space, the great filaments and voids, the clusters and chains, all sculpted by invisible hands. And the space between, once thought to be calm, is accelerating outward with a force that doesn't need stars to shine. We live in a universe of effects without explanations. We know what happens. We just don't know why. And maybe that's what makes it beautiful, that we see only a shimmer on the surface of something vast and hidden, that even with telescopes that can see to the edge of time, we still only glimpse shadows, that most of what exists is conscious, not only out of reach but out of sight. In a cosmos built mostly from the unseen, light becomes a detail, matter becomes a decoration, and our brief moment of awareness becomes something miraculous, not because we understand everything, but because we understand that we don't. We live in a darkness filled with gravity and energy, shaped by mysteries that leave no trace except the structure of everything. The stars shine, but it is the shadow that holds them. When you touch your hand to your chest, it feels solid. When you press your fingers together, nothing slips through. The desk beneath you, the walls around you, your bones, your breath, they all seem real, tangible, dependable. But beneath the surface of everything you've ever known, something strange is happening. Reality, as you experience it, is not what it appears to be. It isn't solid. It isn't firm. In fact, most of it is almost entirely empty. Atoms are the building blocks of matter. Every cell in your body, every tree, every mountain, every star made of atoms. But atoms themselves are not solid balls packed tightly together. They are mostly space. At their core sits a nucleus, incredibly small, dense, and heavy. Around it, electrons whirl in probabilistic clouds, not fixed orbits like planets around a sun, but blurry zones of likelihood. The distance between the nucleus and the electrons, in relative terms, is vast. If an atom were the size of a cathedral, the nucleus would be a grain of sand floating at the center. The rest would be emptiness. And yet, that emptiness makes up you. The solidity you feel when you knock on wood or lean into a chair isn't matter pressing against matter. It's forces, specifically, the electromagnetic repulsion between the electrons in your atoms and the electrons in whatever you're touching. Two objects don't really meet. They resist. They push. And to you, that feels like contact. But at no point do the particles truly collide. They never touch. It gets stranger. Because the particles themselves, protons, neutrons, electrons, aren't really little spheres either. They're better thought of as excitations in fields. According to quantum field theory, the universe is filled with invisible fields that stretch across all of space. Each particle we observe is just a ripple, a small disturbance in its corresponding field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. These ripples carry energy and behave like particles, but they are not made of anything smaller. They just are. The universe, in its deepest layer, is more like a sea of vibrations than a collection of things. You are not made of objects. You are made of patterns, waves, probabilities, places where the energy hums a little louder than the silence around it. And these patterns are unpredictable, even in principle. At the quantum level, particles don't have precise positions or speeds until you measure them. Instead, they exist in a haze of possibility. A particle can be here or there or somewhere in between. Its path is not fixed. It is governed by a wave function, a mathematical blur of where it might be. And when you look, when you measure, it snaps into one place. But even that moment is uncertain. It doesn't happen because of some hidden mechanism. It happens because uncertainty is built into the fabric of reality. This is not an artifact of our tools. It's not a limitation of our knowledge. It is how the universe works. So when you sit still and feel solid and certain, remember that the atoms in your body are mostly vacuum. The protons and neutrons in your cells are built of quarks, held together by gluons, particles that act more like binding energies than physical glue. The electrons around them flit between energy levels in strange, non-local jumps, and the forces that govern them, electromagnetism, the strong nuclear force, the weak force, operate in a realm where cause and effect blur into waves and statistics. And yet, somehow, out of all that uncertainty and emptiness comes the world you know. Tables don't melt into mist. People don't dissolve into probabilities. Reality stabilizes at our scale. The dance of the quantum becomes the structure of the everyday. But the illusion of solidity is just that, an illusion, a trick of scale. What looks fixed is in constant motion. What feels dense is mostly void. If you could remove all the space inside the atoms of every human on Earth, compressing the nuclei together and ignoring the forces that repel them, you could fit all of humanity into the size of a sugar cube. Billions of people, reduced not by cutting or slicing, but simply by removing the nothingness in between. And yet, that nothingness is everything. It gives atoms their size. It gives molecules their structure. It allows light to pass, electricity to flow, heat to transfer. Without the empty space, there would be no motion, no interaction, no existence as we know it. Even your own thoughts, which feel so separate from matter, are patterns of electricity and chemistry rippling through a network of atoms behaving according to the same quantum rules. Your sense of self, of continuity, is built atop a scaffold of temporary alignments. The atoms in your body weren't born with you and won't die with you. They came from stars, drifted through dust clouds, swirled in oceans, passed through plants and animals before becoming part of your momentary shape. They will move on again. In a sense, you are a temporary agreement, a coordination of mostly empty space, holding together just long enough to wonder what you're made of. And the answer is, not much. Not in the solid sense. Not in the classical way. You are mostly space. The universe is mostly space. But that space is alive with potential, energy, and motion. It hums with unseen fields and fluctuations. It whispers with probability. And out of that humming comes you. Not a thing, not a statue, but a process, a pattern, a brief, brilliant resonance in the quiet music of everything. Every breath you've ever taken, every heartbeat, every glance, or touch, or thought, has been made possible by atoms that were forged in the hearts of stars. The calcium in your bones, the iron in your blood, the oxygen filling your lungs as you exhale into the quiet night. They were not born on Earth. They were not crafted in soil or rain or seed. They were born in fire, in cataclysms so powerful they shattered suns and scattered their remains across the galaxy like ash on the wind. You are not just a product of biology or chemistry, you are the afterglow of stars. In the early universe, there were no planets, no trees, no oceans, no people, not even complex atoms, just hydrogen, helium, and traces of lithium. These were the first elements, born in the first few minutes after the Big Bang, when everything was dense and hot enough for nuclei to form, but not yet complex enough to hold together anything more elaborate. For hundreds of millions of years, this was all there was, a dark, cooling expanse filled with simple gases drifting through newborn space. Then gravity began to gather these gases into knots, and those knots ignited. The first stars were massive, short-lived giants. They burned through their fuel in just a few million years, a blink in cosmic time. But in their cores, something remarkable was happening. Under immense heat and pressure, hydrogen atoms fused into helium. That fusion released energy, light, heat, and motion that pushed against gravity and made stars shine. But when the hydrogen was used up, the core contracted, becoming hotter and denser, and began fusing helium into carbon, carbon into oxygen, and on it went building the periodic table in layers, like a cosmic furnace forging raw material out of pure energy. These fusion processes continued until iron was reached. And then, everything changed. Iron doesn't yield energy when fused, it consumes it. So when a star's core fills with iron, the fusion stops. Without outward pressure from fusion, gravity wins. The core collapses in an instant, and the outer layers crash inward. The result is a supernova, an explosion so bright it can outshine an entire galaxy. In those brief moments of unimaginable violence, the temperatures soar high enough to forge elements even heavier than iron, gold, uranium, iodine. The blast flings all of these atoms outward, seeding the interstellar medium with the raw ingredients for everything that would come next. Everything we see today, planets, moons, clouds, creatures, is built from this recycled stardust. The carbon in your DNA, the nitrogen in your muscles, the phosphorus in your thoughts, all of it passed through the belly of a star. And not just one star, but many. The atoms that make you are a patchwork, stitched together from the remnants of multiple stellar deaths over billions of years. You are, quite literally, a mosaic of ancient suns. Eventually, some of that dust settled into a cloud dense enough to form our solar system. As it collapsed, it began to spin, flattening into a disk. At the center, the sun was born, igniting into light. Around it, grains of rock and ice collided, forming planets. Earth was one of them, a tiny marble in a vast new sea. And on this world, the heavy elements joined with energy and water, forming molecules that could copy themselves, respond to change, and eventually become aware. You, a being made not only of matter, but of memory, of curiosity, of stardust, that learned to wonder where it came from. The iron in your blood carries oxygen to your cells. That same iron was forged in the collapsing core of a star that died before our sun was born. The calcium in your teeth once drifted through a cloud of gas, unclaimed, until Earth gave it shape. Every atom in your body has a history, and most of that history unfolded in a place far older, far grander, and far more violent than anything we call home. Even now, the cycle continues. New stars are born from clouds enriched by the dead. Planets form in the shadow of explosions. Life, perhaps elsewhere, stirs from these same ingredients. Somewhere across the galaxy, another being may be looking up into its sky, built from the same remnants, asking the same questions. What am I? Where did I come from? What is this place made of? And the answer, whispered across billions of years, remains the same. You are not separate from the stars. You are their continuation. You are their breath and their residue. You are the light that lingered and cooled and found itself woven into thought. The universe did not build you from the outside in. It built you from within. You are its story, unfolding. You are its memory, made flesh. And every time you close your eyes and feel the weight of your own presence, you are feeling the pull of gravity, the trace of fusion, the echo of distant fire. You are made of stardust, and somehow, impossibly, the stars made something that could look back and see them. Every star you see is alive in a way that feels eternal. They flicker in the night with calm indifference, their light steady, ancient, and constant. But nothing in the universe lives forever. Stars, like everything else, are born, they burn, and they die. And their deaths are not quiet endings, but cataclysms, violent, radiant finales that tear themselves apart so that others might exist. Every breath you take, every atom in your blood, every rock beneath your feet was once inside a star that died to make room for something new. Stars die so others can live. When a star is young, it burns with balance. Gravity pulls its matter inward, and fusion pushes outward. These forces are locked in a perfect truce. Inside the core, atoms fuse together, turning hydrogen into helium, releasing energy in the process, energy that becomes light, heat, and life for anything orbiting nearby. For billions of years, this equilibrium can last, steady as a heartbeat. The sun, right now, is in that phase, but this peace doesn't last forever. Eventually, the fuel begins to run out. When a star exhausts its hydrogen, the core shrinks under its own gravity, compressing and heating until it can ignite helium. For smaller stars, like our sun, this process is gentle. The outer layers swell into a red giant, then drift away, forming a beautiful glowing shell called a planetary nebula. The core that remains collapses into a white dwarf, a dense, fading ember that will slowly cool for trillions of years. It's a quiet death, serene and slow, like a candle burning to the end of its wick. But for massive stars, those many times larger than the sun, the ending is anything but quiet. When they burn through their hydrogen and helium, their cores become hot enough to fuse heavier elements, carbon, oxygen, silicon, all the way up to iron. But iron is different. Fusing iron doesn't produce energy, it consumes it. And so, the delicate balance that has held the star together begins to break. The outward pressure of fusion collapses, and gravity, patient and relentless, takes over. The star's core implodes in a fraction of a second, reaching temperatures of billions of degrees. What happens next is one of the most violent events in the universe. The outer layers crash inward, rebound off the dense core, and explode outward in a supernova. For a brief moment, the star shines brighter than an entire galaxy. Light bursts across space, carrying the signature of new elements forged in the explosion: gold, silver, uranium, iodine. In that instant, the universe enriches itself. Every atom of gold on Earth, every trace of iron in your blood, every shimmer of calcium in your bones was born from such a death. The core that survives a supernova becomes something extraordinary. If the original star was moderately massive, the core compresses into a neutron star, a sphere only about 20 kilometers wide, but with more mass than the Sun. Its gravity is so intense that the atoms inside it are crushed. Electrons and protons fuse into neutrons, forming a solid sea of nuclear matter. A teaspoon of a neutron star would weigh billions of tons. It is matter pushed to its ultimate limit, an object so extreme that light curves around it and time itself distorts in its presence. If the star was even more massive, its core collapses further still, past the threshold of physics, past the ability of matter to resist. It becomes a black hole, an abyss where gravity reigns completely, where not even light can escape. The star, once a blazing beacon of creation, ends as an invisible tear in space. But even then, it is not truly gone. Black holes influence the galaxies around them, shaping cosmic structure, spinning the gas and stars into patterns of order amid the chaos. Death, in space, is never absolute. When a supernova's shockwave tears through the surrounding interstellar medium, it sweeps up clouds of dust and gas, compressing them, stirring them into motion. These shockwaves are midwives for new stars. They trigger the collapse of nearby clouds, setting off new rounds of star formation. Out of the ashes of one star, hundreds more are born. The universe recycles itself endlessly. Matter that once glowed in one sun's heart is reborn in another. The debris becomes planets, comets, moons, and sometimes life. Even our solar system is a product of this cosmic inheritance. Long before Earth existed, a supernova exploded nearby, enriching the gas cloud that would eventually form the Sun. The radioactive elements we find in meteorites, the fingerprints of that ancient blast, prove that our planet was built from the remnants of a dead star. Every atom of gold, every ounce of oxygen, every bit of iron inside you was once dust floating through space, waiting to be pulled into something new. You are made of stellar debris, assembled from ruins. It's strange to think that destruction is the engine of creation, that life depends on death, that the most violent events in the cosmos are also acts of generosity. When stars die, they do not vanish quietly into the dark. They give everything they have. Their last breath fills space with the raw materials for worlds not yet imagined. Without their sacrifice, the universe would remain cold and simple, hydrogen and helium drifting aimlessly forever. Instead, because stars die, there are colors, chemistry, oceans, minds, and music. Because stars explode, there is gold on your finger, iron in your veins, and sunlight on your face. Every atom of you was part of something that burned and broke and scattered across time. You are the continuation of that chain of endings and beginnings. In a very real sense, stars are the ancestors of everything. They live long lives, transform themselves in silence, and when the time comes, they give back all they've created. Every sunrise you've ever seen began in the ashes of another sun. Every moment of life is borrowed light, and somewhere, even now, another massive star is nearing its end. Its core is trembling under the weight of iron, its light flickering as it prepares to collapse. Soon it will go supernova, and its dust will drift for eons before finding new purpose, perhaps as part of another world, another life, another being, staring up at the stars, wondering where it all began. In the universe, nothing truly dies. It changes form, it transfers, it burns and cools and rises again in another shape. Stars die so others can live, and through them, the cosmos breathes. In the stories we tell, black holes are the villains. They devour stars, tear apart planets, and swallow light whole. They lurk at the edge of our understanding, invisible and inescapable, the ultimate symbol of cosmic finality. But the truth, as always in the universe, is more complicated and more beautiful. Black holes are not just destroyers, they are sculptors, engines, anchors. They shape the structure of galaxies, they stir the fabric of space and time, and they may hold the keys to physics we haven't yet begun to unlock. At their heart, black holes are simple. They are regions of space where gravity becomes so strong that escape becomes impossible. Not because the pull is unusually fast or the speed of light unusually slow, but because the curvature of space-time itself folds in on itself. Picture a map of space not as a flat grid, but as a pliable sheet. A planet makes a dent, a star makes a deeper one, but a black hole punctures right through. At a certain distance, called the event horizon, the slope becomes so steep that no path leads out. But the simplicity ends there. When a massive star collapses, its core may compress into an infinitely dense point, a singularity surrounded by that invisible boundary. We can't see the singularity, and we never will. Even light, the fastest traveler in the universe, cannot outrun the gravity within. But we can see what black holes do to their surroundings. We see stars orbiting something dark with impossible speed. We see jets of plasma shooting from galactic centers, powered by invisible engines. We see light twisted, time warped, matter shredded into spirals of glowing gas. Black holes don't just consume, they transform. At the center of almost every large galaxy, including our own, there sits a supermassive black hole. Ours is called Sagittarius A*, and though it's quiet now, it still shapes the Milky Way. Its gravity binds stars in orbit, keeps the core of our galaxy dense and spinning. In more active galaxies, these black holes gorge on gas and dust, releasing vast energy in the process. Ironically, the most luminous objects in the universe, quasars, are powered by black holes. Light brighter than trillions of suns pours from the swirling material falling inward, heating up as it spirals through magnetic fields and friction. The very act of falling becomes a performance of brilliance. Without black holes, galaxies would not form the way they do. They regulate star formation. They clear out gas. They set the pace and shape of their galactic neighborhoods. Like unseen gardeners, they prune and guide. Their gravitational influence ripples far beyond their size, steering the evolution of entire cosmic cities. But their strangest gifts are not in how they shape matter, it's in how they stretch the rules. Near a black hole, the normal flow of time slows. A clock falling into a black hole would appear to freeze as it neared the event horizon, ticking slower and slower from an outside perspective, until it seemed to stop entirely. This isn't a trick or illusion, it's a consequence of Einstein's general relativity. Gravity and time are linked. The stronger the gravity, the slower time moves. If you could hover safely just outside a black hole, time for you would crawl compared to someone far away. Minutes for you might be centuries for them. In theory, black holes could let you glimpse the future, though never return to tell the tale. They show us that time is not constant, that it bends, stretches, and warps depending on where you stand. And then there's the edge of knowledge. Black holes sit at the intersection of our two most successful theories, general relativity and quantum mechanics. Relativity governs the large, the massive, the continuous. Quantum mechanics governs the tiny, the random, the discrete. Both work beautifully in their domains, but black holes force them to meet, and they don't agree. One paradox lies in what happens to information. According to quantum theory, information can't be destroyed. But when something falls into a black hole, it seems to vanish beyond recovery. If the black hole evaporates over time, as predicted by Stephen Hawking, it appears to lose that information completely, violating a fundamental rule of quantum physics. This is known as the black hole information paradox, and it remains one of the deepest puzzles in modern science. Some believe the information is somehow encoded in the radiation as the black hole evaporates. Others suggest it's stored at the event horizon, smeared across a holographic surface. Still others wonder if black holes are windows, tunnels to elsewhere, wormholes, bridges between regions of space, or even between universes. No one knows for sure. What we do know is that black holes are not voids. They are not holes in the way a pit in the ground is a hole. They are places, objects, regions of immense energy and influence. They do not suck things in like vacuum cleaners. You could orbit one safely from a distance, just as the Earth orbits the Sun. Only if you cross the event horizon would the pull become absolute. And even then, the story isn't over. From your perspective, you might fall through the horizon in seconds, unaware that time has slowed for others watching you. To them, your fall would take forever. The light from your final moments would stretch and fade, red-shifted into oblivion. But for you, the journey would continue toward the singularity, toward a place where physics breaks and the laws we know no longer apply. Black holes are not just the end of stars, they are the edge of knowledge. They challenge our understanding of time, space, and reality itself. They force us to ask not just how the universe works, but why. They are puzzles written in gravity, mysteries wrapped in lightless silence. And yet, they are necessary. They give shape to the cosmos. They regulate, organize, energize. They illuminate the deepest truths, not by shining, but by hiding. Not by giving answers, but by forcing better questions. In the heart of darkness, the universe writes its most compelling chapters, and in black holes, it may be writing truths we haven't yet learned how to read. Time, the steady metronome we live by, is not as steady as it seems. On Earth, it feels predictable. It ticks forward with every breath, every footstep, every sunrise and season. But time is not a universal constant. It flows differently depending on where you are and how fast you're moving. It stretches and compresses, warps and twists, not because of malfunction, but because that's how the universe is built. Time and space are not separate entities. They are part of a single fabric, woven together in loops and folds, bent by mass and motion. Imagine holding a clock in your hand. Now imagine taking that clock into space, to orbit above a massive planet, or to ride on a ship accelerating close to the speed of light. If you looked at the clock from a distance, you would see something strange. It would seem to tick slower, not because it's broken, and not because you're far away, but because time itself is flowing more slowly in that place. This phenomenon is called time dilation, and it's a direct consequence of Einstein's theory of relativity. His insight was simple and world-shaking. The laws of physics are the same for all observers, but space and time are flexible. They respond to gravity and motion. They bend around mass and energy. The greater the mass, the deeper the curve in space-time. And where space curves, time slows down. This isn't science fiction. It's been measured. Astronauts aboard the International Space Station orbit Earth at over 28,000 kilometers per hour. Compared to people on the ground, their clocks run just a tiny bit slower. After 6 months in orbit, an astronaut will have aged ever so slightly less than their twin on Earth, just milliseconds, but measurable. It's not a dream or a metaphor, it's reality. Now take that same idea and extend it further. Fly toward a black hole, where gravity is so intense that it warps space like a whirlpool. As you draw nearer, time slows more and more. From your perspective, everything feels normal. But to someone watching from far away, your motion stretches. Your clock appears to freeze. Light leaving your ship gets redder, dimmer, weaker, until it fades entirely. To the outside world, you appear to stop. To yourself, time moves on. The deeper you fall into gravity's well, the more distorted time becomes. The universe is still there, unfolding around you, but you're no longer moving through it at the same pace. Time is not a background stage. It is part of the dance. There's another way to stretch time speed. As you accelerate toward the speed of light, strange things begin to happen. Mass increases, distances contract, and time, again, slows down. If you could travel in a spaceship at near light speed, decades could pass on Earth while only a few years passed for you. You could journey to a distant star, and when you returned, the people you left behind might be gone. Cities changed, languages shifted, oceans risen or fallen, and you would feel untouched. This isn't just a hypothetical thought experiment. It's built into the equations that govern how light, mass, and energy behave. Time dilation isn't an error to be corrected. It's a feature of a universe that does not operate on fixed coordinates, but on relative ones. Everything depends on your frame of reference, your speed, your position, and your gravity. Even here on Earth, time flows differently depending on elevation. A clock placed on a mountain ticks faster than one at sea level. A taller building ages infinitesimally faster at the top floor than at the ground floor. The difference is tiny, but it's real. GPS satellites have to account for both special and general relativity, time dilation from speed and from gravity, just to stay accurate. If they didn't, their signals would drift, and your navigation system would be off by kilometers in just a matter of days. What we call time is deeply tied to where we are and how we move. It is not a universal river, but a shifting, braided stream. It can stretch and contract, fold and ripple. And though we live within its flow, we are only beginning to understand its nature. There are places in the universe near the edges of black holes, inside the throats of wormholes, along the ragged frontiers of the Big Bang, where time may behave in ways we can't yet imagine, where the past and future blur, where cause and effect lose their footing, where time might loop back on itself or split into parallel threads. We don't know yet what's possible, only that time is more flexible, more alive than we ever suspected. And so, we live in a universe where every clock tells a personal story, where your heartbeat, your breath, your aging cells are tuned to the particular gravity well and velocity of your life, and where, in theory, journeys into the far future are not just possible, they're built into the rules. Time travel, in one direction at least, is not a myth. It is encoded in relativity. The faster you move, the less time you experience. You could travel centuries into Earth's future just by accelerating fast enough and waiting. The catch, of course, is getting back. The past, as far as we know, is sealed. Still, the idea that time is not fixed but fluid changes how we see everything. It reminds us that now is not the same everywhere, that the universe has no single ticking clock, that simultaneity, two things happening at once, is relative. It depends on where you are, how you move, and what you observe. So, when you look at the stars tonight, you're not just seeing across distance, you're seeing across time. The light from those stars left them years, centuries, millennia ago. You are always looking into the past, and as you move through space, you shape your future. The universe holds no master timeline, only intersecting paths, each carved by motion, mass, and mystery. And somewhere in that tangled web, you are walking your own thread, your own slice of time curving gently through the cosmos, like starlight bending through gravity. When you look up at the night sky, it's tempting to imagine yourself at the center of something vast. The stars seem to encircle you in every direction, forming a cosmic dome that curves over the Earth like a protective shell. The moon rises, the planets drift, the Milky Way stretches overhead like a luminous river, and you stand beneath it all, grounded and still. But in the universe, there is no true center. There is no up or down, no absolute left or right. The cosmos is not built like a snow globe, with Earth nestled in the middle. It is more like a boundless ocean, expanding in every direction at once, with no edge and no special vantage point from which everything else unfolds. This may sound counterintuitive, because our everyday lives are full of orientation. We build floors and ceilings, we label maps with cardinal directions, we plant our feet on ground that feels immovable, and we treat the sky as a canopy above us. But all of these directions are local. They're true only relative to the surface of our spinning planet. In space, there is no universal up. A spaceship pointed north by Earth standards will seem upside down to someone viewing from another galaxy. Everything floats in motion, and the frame of reference is always shifting. And the idea of a center, the notion that somewhere, if you looked far enough, you might find the origin point of the cosmos, is just as misleading. The universe isn't expanding into anything. It's not like a balloon blowing up in empty space, with some central spot where it all began. Instead, space itself is stretching, everywhere, all at once. Every galaxy sees every other galaxy moving away, not because they're fleeing a single explosion, but because the space between them is growing. If you were to rewind time, you would find that all matter and energy were once compressed into a hot, dense state, what we call the Big Bang. But the Big Bang didn't happen at a point. It happened everywhere. Every region of space today was once part of that initial fire. The center of the universe isn't some distant coordinate hidden behind a cluster of galaxies. The center was where you are, and where I am, and where every galaxy now floats. The expansion began not from a place, but from a state. If you stood on a distant world, orbiting a star in a galaxy 100 million light-years away, the view would be much the same. You'd see galaxies stretching in all directions, moving away from you. And if you asked whether you were at the center, the answer would be yes, but only in the same way it would be yes from here. Every point in space can be treated as the center, because the laws of physics work the same everywhere. There is no preferred location, no cosmic throne, just motion, distance, and light traveling across the dark. This idea that there is no central point, no universal direction, no fixed place to stand can be disorienting, but it's also liberating. It means we are not on the edge of something grand. We are part of it. Not above or below, not behind or ahead, but within. Our galaxy spins in a web of other galaxies, which move with the expansion of space, which follows rules that apply to every corner of the cosmos. We are not in a privileged location, but we are also not isolated. The universe has no center. It simply is everywhere at once, expanding, unfolding, carrying stars and atoms and thoughts along with it. And in this strange, directionless sea, we have found our bearings, not through position, but through curiosity, through the ability to ask, again and again, not just where we are, but what it means to be anywhere at all. In the cold silence between the stars, galaxies drift like islands through a cosmic sea, separated by millions of light-years, but drawn together by a slow and ancient pull. They appear still to our eyes, frozen in place against the black, but they are not. Galaxies move, they orbit, tumble, and sometimes they collide. But this isn't a collision in the way we think of one. There is no crash of metal or shattering of glass. There is no thunderclap, no explosion that lights the sky. Instead, two enormous collections of stars, each containing hundreds of billions of suns, pass through each other like ghosts, gliding in silence, barely touching. It sounds impossible, but that's the strange nature of scale in the universe. Galaxies are made mostly of empty space. Stars, even packed into spiral arms and bright cores, are separated by vast distances. If the sun were a ping-pong ball, the next nearest star would be another ping-pong ball more than 1,000 kilometers away. So when two galaxies approach, drawn together by gravity across aeons, the chances of their stars physically colliding are vanishingly small. They pass through each other with quiet grace, like dancers weaving without ever brushing fingertips. But while the stars don't often touch, the galaxies themselves do change. Their shapes distort. Gravitational tides stretch out long streamers of stars, pulling spirals into ribbons and tails. Dust and gas, the unseen scaffolding of galaxies, does collide, and when it does, it compresses, triggering bursts of star formation. In those dense knots, new suns are born in glowing clouds, lighting up regions of space that were once dim and dormant. A collision, for a galaxy, is not destruction, it's transformation. This is what lies in our future. The Milky Way, the galaxy we call home, is on a slow, inevitable course toward its neighbor, the Andromeda Galaxy. Right now, they are over 2 million light-years apart, gliding toward each other at around 400,000 kilometers per hour. It will take about 4 billion years before they meet, but when they do, the result will not be the end of our galaxy. It will be a beginning. They will merge, reshape, and settle into something new. A vast elliptical galaxy, serene and rounded, with stars from both families now circling a common center. The night sky, for future Earth, if Earth still exists, will be profoundly different. Andromeda will grow brighter over generations, becoming a glowing smear across the heavens. Eventually, the two galactic cores will appear side by side, then begin to swirl together in a slow spiral, filling the sky with light and motion. It won't happen in a single night or a single year, but across millions of years, as the galaxies pass through each other again and again, drawn by gravity into one shared future. And even then, most stars will survive untouched. Our solar system might be flung into a new orbit or drift farther from the center, but the planets will remain bound to the sun, circling quietly through the merger. The cosmos does not rush. It changes on scales too vast for one lifetime, or even 1,000, to truly witness. But we can glimpse the process in other galaxies, caught in the act by our telescopes. Great spirals intertwined, filaments stretching between them, glowing pockets of newborn stars blooming in the wake. In these mergers, beauty is born from chaos. Symmetry dissolves into complexity. Galaxies twist into shapes that look more like brushstrokes than structures, painted in light and time. Some look like tadpoles, with long trailing tails. Others form luminous rings, or warped crescents that seem to ripple with motion. These are not accidents. They are the natural result of gravity's choreography, of billions of stars responding to forces deeper than any mind can fully grasp. And sometimes, at the center of each galaxy, supermassive black holes collide as well. As the galaxies merge, their central black holes spiral toward each other, wrapped in invisible gravity, dancing a slow and final spiral until they coalesce. The energy released in such an event is extraordinary, sending ripples through the fabric of space-time gravitational waves that echo across the universe. We have only recently begun to detect these waves, listening for the shudders of space itself as galaxies whisper their ancient stories. So when you look up and see the stars, when you think of the night sky as still, as permanent, remember that it is anything but. Everything is moving. Everything is changing. And one day, the sky will be filled not just with stars, but with the luminous swirl of another galaxy sliding through our own. The universe does not shatter when it collides. It sings. In gravity's quiet language, it reshapes itself again and again, always becoming something new. And though the stars pass like ghosts, untouched, the echoes of their journey are written in light. There's a planet where the sky doesn't just rain, it cuts. A place where the clouds carry molten glass, and the winds whip sideways at thousands of kilometers an hour. It's called HD 189733b, and it's not a world of gentle sunsets or rolling oceans. It's a nightmare stitched into the fabric of the cosmos, shimmering blue like Earth from afar, but betraying none of our familiar comforts up close. This is a place where the air is heavy with vaporized silicates, and where the weather doesn't soothe its slices. HD 189733, B orbits its star so tightly that a year there lasts just over 2 days. That closeness scorches the planet, baking its atmosphere to over 1,000 degrees Celsius. But this hellish heat isn't evenly spread. The planet is tidally locked, meaning one side always faces the star, endlessly scorched, while the other remains in perpetual night. The result is a deep and eternal tension between extremes, one hemisphere constantly boiling, the other shivering in shadow. Winds howl across this divide at supersonic speeds, redistributing heat and flinging molten particles from light into darkness. And in those winds, carried aloft in a furious ballet of vapor and velocity, are microscopic shards of glass, not in the way we know glass here on Earth, fragile, clear, delicate, but as vaporized silicate minerals, suspended in the air like dust until they cool and crystallize into sharp-edged droplets. In the chaos of the storm, these droplets rain sideways, scouring anything in their path. If you could stand there, and of course, you couldn't, your body would be shredded before you could draw a breath. The atmosphere alone would crush you, roast you, then flay you apart. And yet, from over 63 light-years away, we can see this world. We've measured its color, inferred its weather, and traced the pattern of its winds by the way it dims the light of its star during transit. This is the kind of clarity modern astronomy can now provide, not only the existence of distant planets, but a glimpse of their very skies. With sensitive instruments, we can detect the chemical fingerprints left behind as starlight filters through their atmospheres. From a flicker of light, we deduce an entire alien climate, and HD 189733b is just one example. The universe is littered with planets that break the rules we once thought were unbreakable. There are worlds made of pure diamond, gas giants that orbit their stars in a matter of hours, planets that drift alone, unbound to any star, wandering the galaxy like ghosts. One known as WASP 1-2b is so close to its host star that it's being stretched into the shape of an egg, its mass siphoned off by gravity like a candle melting in slow motion. Another, GJ 1214b, may be an ocean world covered entirely by a steamy, crushing ocean hundreds of kilometers deep, with pressures and temperatures that defy human intuition. We used to believe that planets like Earth were special, that the recipe for life required a narrow set of ingredients: the right temperature, the right orbit, a rocky surface, liquid water. And while Earth remains the only known harbor of life, what exoplanets like HD 189733b teach us is that the universe is far more imaginative than we are. It doesn't follow familiar blueprints. It experiments wildly, creating environments that seem drawn from myth or fever dreams, places where the skies glow with metallic storms and the ground may never have existed at all. The question is no longer whether strange planets exist, it's how many and how strange. We've discovered thousands of them, scattered across the Milky Way, and the catalog grows every year. Some orbit twin stars, caught in a perpetual dance between two suns. Others skim so close to their stars that their atmospheres are stripped away, leaving bare, irradiated cores. Some are puffed up like balloons, enormous in size but light as foam, while others are so dense they may be made of exotic matter compressed beyond our experience. And all of them are quiet. They don't announce their oddities. They wait, silently orbiting in the dark, until our telescopes catch the flicker of their transit or the wobble of their star. From those tiny signals, we uncover stories that stretch the boundaries of what planets can be. We find worlds that rewrite our definitions, that remind us the cosmos isn't built for our comfort or expectations. It is endlessly inventive and utterly unconcerned with what makes sense to us. So when we imagine alien worlds, we must leave behind our notions of blue skies and green grass. The real exoplanets are stranger than fiction. They rain molten glass sideways. They shimmer with clouds of iron. They spin in darkness or bake in eternal noon. and still they orbit on, carried by gravity and time, each one a quiet marvel stitched into the fabric of a universe that never runs out of surprises. In the vastness of space, between galaxies and stars, in the emptiest pockets of the cosmos, temperatures drop to extremes that no living thing could survive. Out there, in the vacuum that stretches beyond the reach of starlight, the ambient temperature hovers just above absolute zero, about 2.7 degrees Kelvin, or negative 270.45 degrees Celsius. It is a cold so deep, so pure, it feels like the universe's breath has been held since time began. You might think nothing could be colder than this, the background chill of the cosmos, the afterglow of the Big Bang itself. But you would be wrong. The coldest places we know of are not in the distant reaches of intergalactic space. They're here, on Earth, inside laboratories built by human hands, where researchers bend the laws of nature to create temperatures colder than the vacuum of space. In these tiny, carefully isolated chambers, scientists have reached within a billionth of a degree above absolute zero, the lowest temperature that the laws of physics will allow. Absolute zero is not just a number, it's a boundary. At 0 Kelvin, all motion stops. Molecules no longer vibrate. Atoms sit still. Energy drains away until there is nothing left to lose. But according to quantum mechanics, even that total stillness is unreachable. There's always a trace, a whisper of uncertainty. Particles can never be perfectly frozen because the very act of being demands motion, however slight. So scientists chase the edge, not to reach zero, but to get as close as the universe will allow. And in doing so, they create some of the strangest matter in existence. When atoms are cooled to near absolute zero, they begin to behave less like individual particles and more like waves. At these temperatures, matter stops acting the way we expect. It becomes something collective, cooperative. A new state of being emerges, known as a Bose-Einstein condensate, a quantum soup where individual atoms overlap and blend, losing their separate identities. They begin to act as one. You could take 1,000 atoms and cool them until they become a single entity, a cloud of matter that moves as a unified wave, spread out in space, yet governed by a single quantum state. It's as if a crowd of people suddenly began thinking, breathing, and walking in perfect harmony, not because they were told to, but because their very nature changed. This is not just a curiosity. It's a glimpse into the fundamental fabric of reality. It's a way to study the quantum world on a human scale, to stretch time, slow motion, and peek into the mechanics of the universe at its most delicate. To reach these temperatures, scientists don't use ice or wind. They use lasers. Strangely, beams of light often associated with heat are the tools that cool atoms to such extraordinary depths. It works by carefully tuning the lasers to oppose the motion of atoms, like a cosmic game of catch, where each photon thrown at an atom slows it down just a little more. As the atoms lose speed, they lose heat. Slower motion means lower temperature, and the colder they get, the more precisely we can see the quantum fog that surrounds everything. These frigid experiments don't require giant machines spanning continents. Some of the coldest temperatures have been created in rooms the size of an office. What they do require is patience, precision, and a willingness to explore a world where the ordinary rules break down. Because at these temperatures, the strange becomes normal. Superfluid helium climbs walls. Electrons pair up and flow with zero resistance. Atoms tunnel through barriers they should not pass. The quantum rules we usually ignore become vivid, impossible to overlook. In 2018, NASA launched a device called the Cold Atom Laboratory aboard the International Space Station. Suspended in microgravity, freed from Earth's pull, it was able to cool clouds of atoms to record-breaking lows colder than anything naturally found in space. In orbit, without the interference of gravity or atmosphere, atoms can be held still for longer, studied with greater clarity, and pushed further toward that impossible limit. It's a reminder that even in the age of interplanetary ambition, our greatest frontiers may still lie within, at the scale of the invisible. Cold is not just an absence of heat, it is a frontier of knowledge. The colder we go, the more we see into the subtle gears that turn the universe. The cold reveals symmetry, coherence, unity. It strips away thermal chaos and allows the hidden structure of matter to emerge. In these moments, reality becomes crystalline, not hard and sharp, but orderly, calm, and strange. And yet, even in these carefully controlled environments, sealed chambers, laser traps, magnetic fields, the temperature never truly reaches zero. There is always movement, always uncertainty, always a tremor in the silence. Because the universe will not stop. It will not be frozen, not completely. It will always keep a spark alive, hidden in the smallest spaces, echoing the rule that to be is to move, however gently. So when we talk about the coldest places in the cosmos, we must not look only to the stars or the void between them. We must look to ourselves, to the minds and hands that have dared to bottle starlight and silence, to freeze time and motion, if only for a breath. Because the coldest place is not out there, it is here. Not in the emptiness of space, but in the curiosity that burns hot enough to chase the cold. In the deep quiet between stars, there are planets with no sun, no orbit, no dawn. They drift alone through the galaxy, untethered and unseen, moving silently through a darkness so complete it would swallow even the faintest glimmer of light. These are the rogue planets' worlds that once may have belonged to star systems, but were flung out, exiled by gravity's violent rearrangements. Or perhaps they never belonged at all. Perhaps they formed in the dark from scattered dust and gas, far from the warmth of any star, born into solitude. They are not rare. In fact, there may be more of them than stars. Billions, maybe trillions of lonely planets, drifting between suns, like forgotten stones in an endless ocean. They do not glow, they do not shine. And so, for most of human history, we didn't know they were there. Our telescopes are built to catch light, and these planets offer almost none. They are cold, faint, cloaked in shadow, but they have mass, they have gravity, and gravity bends light. When a rogue planet passes in front of a distant star, it can act like a lens, briefly magnifying the starlight behind it. These brief flickers, subtle, sudden, unrepeatable, are how we've begun to find them. Imagine a world like Earth, cast adrift. The sun, once a constant presence in the sky, is gone. The days no longer come. There is no orbit to keep time, no seasonal tilt, no rising or setting of light. The planet spins on, but the sky remains black. Oceans freeze. Atmospheres collapse into frost. Life, if it ever existed, retreats deep underground or disappears entirely. And yet, not all warmth is lost. Some rogue planets may still harbor heat, remnants from their formation, or stirred by radioactive decay in their cores. A few might even have subsurface oceans beneath thick layers of ice, warmed from within, hiding secret chemistries in their lightless depths, and that means they might not be lifeless after all. Life on Earth is married to sunlight. It feeds on it, grows in it, reaches toward it, but there are places on our own planet far beneath the ocean, around hydrothermal vents, where life thrives without sunlight. There, in the black pressure of the abyss, bacteria feast on minerals and heat. Entire ecosystems form around them, strange and self-contained. If it can happen here, it might happen there, on a planet with no sky, no sun, no stars to steer by just rock, ice, and time. Some of these rogue worlds are giants, the size of Jupiter or larger, with thick atmospheres and storm systems that rage in perpetual twilight. Others may be small and rocky, scarred by impacts or sheathed in glaciers, and some could be unlike anything we've imagined. planets sculpted by strange conditions, shaped not by starlight, but by the void itself. With no sun to strip away lighter gases, some may retain thick blankets of hydrogen, creating pressure cookers where exotic chemistry unfolds. These are not failed planets or broken ones. They are simply different, untamed, unanchored. The Milky Way is full of them. Between the bright pinpoints of stars, these silent travelers pass unseen. They do not announce their presence. They leave no trail. But they are there, scattered across the dark, like seeds without soil. They remind us that not all worlds are nestled in the glow of a parent star. Not all stories follow the familiar script. Some wander, and their journey can last forever. Without a star to slow them, without a system to hold them back, rogue planets drift through space for billions of years, curving slowly through the galaxy's gravity well. Some may eventually pass near a star again, briefly warmed, perhaps even captured. Others will roam until the end of time, locked in night, bearing silent witness to the changing face of the cosmos. We are used to thinking of planets as secondary things, children of stars, orbiting, dependent, defined by the light they receive. But rogue planets defy that. They exist without that relationship, without the daily rhythm of sunrise and sunset. They are not lesser because they drift. They are simply alone, and there is a kind of awe in that, an elegant defiance, a reminder that the universe does not require our permission to be strange. One day, we may visit one, send a probe, or a ship, or even a crew. Land on a frozen plain beneath a black sky, listen to the deep silence, feel the weight of a world that never knew sunlight. It would be a moment of profound stillness, the first spark of human awareness touching a world that has never been warmed by morning. But for now, they drift, homeless, starless, wrapped in darkness and secrecy. We catch glimpses as they pass, brief gravitational signatures, flickers of possibility. And we wonder how many there are, how many stories they could tell, how many hidden oceans, how many chemical dances, how many chances for something like life waiting in the dark. Not all paths circle a light. Some lead away, into the silence, into the unknown. And the universe, it seems, has room for both. If you could strip the universe of all its stars, all its planets, every last galaxy and cloud of gas, if you erased it all and stood alone in the emptiness, you'd still be surrounded by light. Not light you can see with your eyes, but light that's always there, cool, ancient, and faint, stretching across every corner of the sky. It's not from stars or galaxies. It's from the beginning, a soft, pervasive whisper left over from the moment everything began. This is the cosmic microwave background, and it is the oldest light in the universe. It's not the kind of light that dances or dazzles. It's not a beam or a flash. It's a glow, a presence, a cold, uniform bath of radiation that fills all of space. If you tune a radio to static, a small part of that hiss is the echo of the Big Bang, still humming quietly through the fabric of reality. It's everywhere, no matter where you point your instruments. Above you, beneath you, behind the stars, in the dark between galaxies. It is the afterglow of creation itself. About 13.8 billion years ago, everything we now see, every cluster of galaxies, every breath of interstellar dust, every heartbeat, was packed into something smaller than an atom, an impossible density, an unbearable heat. And then it expanded, not into empty space, but into itself. Space itself unfolded. Time began ticking. Matter took form. In that first searing instant, temperatures were so high that particles couldn't even bind together. It was not a universe of stars or planets. It was a storm of raw energy, roaring with light, where nothing could hold still long enough to become anything solid. For hundreds of thousands of years, the universe remained opaque, too hot for atoms to form. Photons, the particles of light scattered constantly off electrons, bouncing in every direction like sunlight through a fog. The cosmos glowed, but that glow couldn't travel. It was trapped, tangled, hidden in the chaos. But then, slowly, the universe cooled. Around 380,000 years after the beginning, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, light could move freely. It was a quiet release, a letting go. The fog lifted, and the light that had been trapped since the beginning was finally free to travel. That light has been moving ever since, stretched by the expansion of space, thinned and cooled until it became the gentle microwave background we detect today. It's not bright anymore. The glow that once blazed like the surface of a star now measures just 2.7 degrees above absolute zero. But it's still there, and it still carries the fingerprint of those early moments. Tiny fluctuations, minute variations in temperature and density dot the microwave background like freckles on the sky. They are the seeds from which galaxies would grow. The faintest asymmetries, frozen in time, became the scaffolding for everything that followed. When scientists first detected the cosmic microwave background in 1965, they didn't know what they'd found. Two radio engineers, Arno Penzias and Robert Wilson, were testing a new antenna and noticed a persistent noise. No matter where they pointed it, the static remained. They cleaned the equipment, chased pigeons out of the dish, but the signal never vanished. It was, in fact, the universe speaking. The leftover radiation from the birth of everything, washing over the earth in a quiet, ancient rain. Since then, we've mapped it in extraordinary detail. Satellite missions like COBE, WMAP, and Planck have revealed its structure. An all-sky image of the infant universe, captured in soft, glowing patterns. And from those patterns, we've learned how old the universe is, what it's made of, how fast it's expanding, even how it might end. All from a foggy picture of what the cosmos looked like when it was just a baby, still cradled in the warmth of its beginning. It is strange to think that the universe remembers, that even now, billions of years later, the glow of its first light continues to echo through every inch of space. We live inside that echo. Every breath you take is surrounded by it. It's older than the stars, older than the atoms in your body. It has seen everything and forgotten nothing. And though we call it background radiation, that name doesn't do it justice. It's not just background, it is the canvas, the first record, the original light by which we chart the path from chaos to cosmos. It connects us to a time so distant it can barely be imagined. A time before galaxies, before gravity had sculpted the universe into anything recognizable, when everything was still unfolding, still deciding what it might become. That this light still exists is a kind of miracle, that we can detect it, read it, and trace our story through its glow and even greater one. It reminds us that nothing truly vanishes, that the past lingers, not as memory, but as presence, that the universe, for all its silence, still sings the song it sang at the start. So next time you look up into the night sky, remember that you are not just seeing stars. You are standing in the afterglow of creation, bathed in the echo of a moment that gave birth to time itself. And even now, that light is still traveling, still unfolding, still warming the empty spaces with the faint, persistent memory of how everything began. The part of the universe we call home is unusually quiet. If you zoom out far enough beyond Earth, beyond the moon, past the sun and its planets, past the icy debris drifting in the shadows of our solar system, you begin to see the larger architecture of space. Galaxies stretch out in filaments and webs, gathering in luminous clusters, their arms like veins of light threading through the blackness. But nestled in the gaps between these structures, there are vast regions that seem nearly empty, and our Milky Way, with all its hundreds of billions of stars, lies inside one of these gaps, a cosmic void. This might sound paradoxical. How can we be in a void when we're surrounded by stars? But a void doesn't mean absolute emptiness. It means less. Fewer galaxies, fewer stars, less mass. Imagine the universe as a sponge, dense in places where the sponge is thick, airy, in others where bubbles expand. Our corner of the cosmos is one of those airy bubbles, a region with less matter than average, stretching for hundreds of millions of light years in all directions. It's called the local void. This strange emptiness wasn't obvious at first. For most of human history, we had no idea there were such structures in the universe at all. The stars we could see seemed evenly scattered. Even when we began to detect other galaxies, we didn't yet grasp the broader shape of things. But as our instruments improved and our surveys deepened, a pattern began to emerge. Galaxies weren't distributed randomly. They clumped and gathered, forming walls and strands and knots, like frost patterns on glass. And between them, immense gaps yawned. It turns out we live on the edge of one of the largest of these gaps. The local void spans at least 150 million light-years, maybe more. Our galaxy is perched right near the boundary, next to a denser region called the Virgo supercluster. And just like water rolls downhill, galaxies flow out of underdense regions and toward overdense ones, tugged along by gravity. Our galaxy isn't just spinning and expanding, it's also drifting, slowly but surely, away from the void and toward the crowded clusters beyond. This quiet neighborhood may help explain why the night sky appears the way it does. The darkness between stars, the seeming solitude of our position. If we were deep inside a galaxy cluster, with dozens of galaxies packed close together, the night might shine with more diffuse light, more interactions, more gravitational chaos. But here, on the edge of emptiness, things move more slowly. We are less crowded, less disturbed. The emptiness around us also tells a story of time. Voids are places where matter didn't gather, where density fluctuations in the early universe left behind low spots that never quite caught up. Over billions of years, gravity pulled matter toward the high points, away from the valleys, deepening the contrast. The result is the cosmic web we see today, threaded filaments and bright knots of galaxies, separated by these haunting expanses. In some ways, living in a void is a gift. It provides a kind of clarity. Light from distant galaxies reaches us with fewer obstructions. Cosmic rays and radiation flow more cleanly. And as observers, we benefit from the quiet. We can look outward, study the universe's structure, map the patterns and motions, because we are not lost in the noise of a crowded environment. We stand on a kind of cosmic overlook, gazing into the swirl from a place of stillness. But it's also humbling, because even the void is not truly empty. It contains dark matter. It holds scattered particles, rarefied gas, the invisible scaffolding of gravity. It is threaded with filaments too faint to see, inhabited by galaxies too distant to detect. The silence is not absence. It is distance. It is the sound of matter spread thin across unfathomable scale. Sometimes, when we picture the universe, we imagine it brimming with wonders, supernovae, quasars, nebulae bursting with light. And those things exist, but they are balanced by quiet, by space, by the long stretches where nothing seems to happen. This balance between fullness and void is what gives the universe its shape. It is not a mistake or a leftover. It is part of the design, and our place within that design is neither central nor peripheral. We are not in a hub of activity, nor lost in the middle of nowhere. We're on the edge of something vast and quiet, moving towards something brighter. A galaxy with stars and planets and thoughts, drifting along the contours of gravity, riding the slow currents of the cosmic sea. In the void, time feels different. The expansion of space unfolds with less resistance. Galaxies stretch further apart. Light takes longer to arrive. But this, too, is part of the story. Because even here, in this underdense pocket of the universe, life emerged. Intelligence, wonder, the capacity to look into the darkness and ask what it means, and to realize that the void is not a place to fear, but a space that made our seeing possible. We live in a cosmic void, but from here, we see everything. Right now, without you noticing, trillions of particles are slipping through your body. They pass through the walls around you, through the earth beneath your feet, through oceans and mountains and sky. They glide through flesh and bone like shadows through mist, touching almost nothing, leaving almost no trace. These are neutrinos, ghost particles born in the heart of stars, in the violent deaths of suns, in the radioactive decay of matter itself. And though they flood the universe in unimaginable numbers, they are almost impossible to catch. A single breath holds more weight than all the neutrinos that pass through you in a lifetime. They have mass, but barely. They move close to the speed of light, but without light's brilliance. They carry energy, but with almost no consequence. They are the quietest messengers of the cosmos, whispering ancient stories in a voice so faint we almost missed them entirely. They were predicted before they were seen. In the 1,930 seconds, scientists studying radioactive decay noticed something strange. Energy seemed to vanish. The laws of physics, which demand balance, appeared to be broken. But instead of rewriting the laws, physicist Wolfgang Pauli suggested something radical, that another particle was involved. One that was invisible, undetectable, yet essential. A hidden participant that carried away the missing energy. It took decades before we could detect them directly. And even now, it's like trying to catch a shadow with a net made of light. Neutrinos come from everywhere. Most of the ones passing through you right now were born in the sun, forged in the nuclear furnace at its core. Every second, it emits billions of them for every square inch of your body, like a gentle, invisible rain. But others are more ancient. Some were created moments after the Big Bang, part of the first breath of the universe itself. Others arrive from supernovae, cataclysmic explosions that light up galaxies, releasing floods of neutrinos before their light even reaches us. Some come from cosmic rays striking our atmosphere. Some, we suspect, may come from black holes or other exotic sources we have yet to understand. And still, they pass unnoticed. Most particles, protons, electrons, even photons interact with the world around them. They bounce, collide, absorb, reflect. But neutrinos are different. They are affected only by the weak nuclear force and gravity, two of the gentlest forces in nature. This means that out of the trillions streaming through you, maybe one or two will ever interact with a single atom in your body during your entire lifetime. The rest will slip past, unbothered, unseen. To find them, we have to go to extraordinary lengths. Deep underground, beneath mountains and in old mine shafts, we build massive detectors filled with thousands of tons of water or other special fluids. These places are shielded from other particles and background noise, quiet enough to hear the crash, faintest echo. And when a rare neutrino finally does interact, it creates a flash of light just for an instant. That flash is a signature, a fingerprint of something ghostly and ancient brushing against the present moment. From these flickers, we've begun to piece together their story. We've learned that there are at least three kinds: electron, muon, and tau neutrinos, and that they can change from one type to another as they travel, like dancers switching masks in the dark. We've discovered that they have mass, which was once thought impossible. And though we don't know how much, we know it's tiny. So tiny, it's almost nothing. But not nothing. That small difference matters, because the universe is full of neutrinos. For every proton or neutron, there are billions of them. They may not clump together into stars or planets. They may not shine. But their mass, spread across the cosmos, still adds up. They influence the evolution of galaxies. They affect the early growth of the universe. And they may hold the key to mysteries we haven't yet solved, like why the universe is made of matter instead of antimatter, or what dark matter really is. They are everywhere, and they are silent. It's strange to think that something so small, so elusive, could be so important that the universe could be full of particles that barely interact with anything and yet still help shape everything. But that's what neutrinos are. Evidence that not everything needs to be loud to be powerful, that not all forces need to be violent to leave an imprint, that sometimes the quietest things in the universe are the most profound. So tonight, as you sit beneath the stars or drift off to sleep, remember that you are never truly still, that even in the deepest silence, there is motion, there is passage, there is a river of ghost particles flowing through you, through the planet, through every stone and sea and star. They do not stop, they do not rest. They are the invisible witnesses of everything that has ever happened, and they are passing through you now. High above, scattered like luminous grains of salt across the black velvet of the sky, there are stars that do not burn with steady light. Instead, they beat, not in sound, but in rhythm, a slow, silent, pulsing, expanding and contracting, brightening and dimming, like some immense celestial breath drawn over days or weeks. These are Cepheid variables, stars that pulse like hearts, keeping time not just for themselves, but for the universe itself. From a distance, they appear like any other pinprick of starlight, constant, eternal. But watch closely, and you'll notice the change. The steady rise and fall of their brightness follows a precise and predictable pattern, a cosmic metronome ticking across vast distances. It is not random, it is not chaotic. It is a signal, a heartbeat coded in light. Their outer layers expand outward, growing cooler and dimmer, then collapse inward again, heating up and glowing more intensely. This oscillation, this living rhythm, repeats over and over, like the inhale and exhale of something ancient. And in a way, they are alive not in the way we understand life, but in their behavior, in their cycles, in their ability to adapt and change and respond to the physics written into their core. They are massive, far larger than our sun, and nearing the end of their stellar lives. Their fusion furnaces, once balanced and calm, now burn with instability, creating layers that heat and cool in waves. These pulses are not explosions, not spasms, but elegant fluctuations born from the delicate interplay of temperature, pressure, and gravity. What makes them extraordinary is not just their beauty, but their utility. Cepheids are timekeepers. They are rulers stretched across the darkness, helping us measure the cosmos. More than a century ago, astronomers discovered a profound relationship in their light. The longer the period of the pulse, the brighter the star. And because brightness fades with distance, this allowed scientists to compare a Cepheid's known true luminosity to how dim it appears from Earth. Like reading the wattage of a bulb from across a field, they could now calculate how far away the star truly was. For the first time, we had a way to measure the universe not in theory, but in practice. This discovery opened everything. In the early 20th century, when most astronomers believed the Milky Way was the entire universe, a woman named Henrietta Swan Leavitt meticulously studied variable stars in distant clouds of gas and dust. She found the pattern, the relationship between period and brightness. Her quiet, careful work transformed how we understand the cosmos. Using her insight, Edwin Hubble observed Cepheid variables in what was then called the Andromeda Nebula, and from their faint light, he realized something staggering. Andromeda wasn't part of the Milky Way. It was a galaxy of its own. This one, discovery shattered the boundaries of the known universe. Suddenly, we were no longer alone in a sea of stars. We were one galaxy among billions, adrift in a far grander ocean than we had ever imagined. and the stars that pulsed like hearts had shown us the way. Today we still use Cepheid variables to measure distance. They are cosmic lighthouses, blinking out their messages across millions of light years. With them, we can map the shape of the universe, track its expansion, and peer into its history. Their pulses have helped us discover how fast galaxies are moving away, and in doing so, revealed the mysterious presence of dark energy pushing everything apart. They are, in many ways, the universe's own clockwork, not rigid or mechanical, but organic and persistent. Their light arrives here, sometimes millions of years after it began its journey, still carrying the rhythm of its source. It flickers gently into our telescopes, into our instruments, into our understanding. It says, "I was here. This is how far. This is how long." And there is poetry in that something so far away, so vast and remote, can keep such perfect time. That stars can act as storytellers, encoding the shape and age of the cosmos into their own pulses. That without them, we might still believe our galaxy was all there is. But they are more than tools, more than data points. When you look up at the sky and imagine that some of those stars are gently pulsing, breathing, shifting in brilliance with a rhythm that spans days or weeks, it changes how you see the night. It softens it. You realize that even the stars are not static. They are dynamic, alive with motion. And within that motion lies truth. Cepheid variables do not shout. They do not erupt like supernovae or warp space like black holes. They simply pulse, steadily and reliably, across the dark, and in doing so, they bring the universe into focus. They remind us that distance can be measured, that time can be known, that light can carry meaning even when it has crossed millions of years to reach us. So when you next find yourself beneath the stars, think of the ones that breathe, the ones that beat like hearts in the silence. Somewhere out there, a star is pulsing right now, dim, then bright, then dim again, its message still on its way. A rhythm older than memory, carrying across the void, waiting to be seen, waiting to be understood. The universe is not silent. Though it stretches across a vacuum where sound cannot travel, it is filled with rhythm and resonance, with tremors and waves that ripple through the very fabric of reality. These are not the kind of sounds we can hear with ears, but vibrations of space itself, deep, slow, and immense. Born from cataclysm and gravity, these waves carry stories across galaxies. And at the heart of many of those stories are black holes, not just as destroyers, not just as endings, but as instruments. Because black holes can sing, this song is not made of air or pressure. It is made of motion, of space-time flexing like a drumhead, stretched taut by mass and energy. When black holes collide, the energy released is so great that it sends ripples outward, compressing and expanding space itself. These are gravitational waves, waves in the sea of existence, and when they pass through us, they briefly change the length of everything they touch. Distances stretch and contract, though the effect is infinitesimally small. It takes technology of extraordinary precision to detect them. But once we did, we realized we had been deaf to a symphony playing all along. The first note we ever heard came in 2015. Two black holes, each dozens of times the mass of our sun, spiraled inward toward each other in a distant corner of the universe. As they danced closer, their orbit quickened. They circled hundreds of times per second, the force between them unimaginable. And when they finally collided, they released more energy in that one moment than all the stars in the observable universe combined. That energy radiated outward as gravitational waves, an invisible echo through the cosmos. It took 1.3 billion years to reach Earth, and when it did, it nudged the detectors at LIGO, two immense instruments on opposite sides of the United States, just enough to be noticed. The signal was brief, less than a second, but it was distinct. a rising chirp in frequency, like a soft swoop of a violin string, ending in silence. The final ring-down of space-time itself, that chirp, that moment, was the first time humanity ever heard the music of black holes. Gravitational waves don't just tell us that something happened. They tell us what happened. How massive the black holes were. How far away. How fast they spun. It's like reading a fingerprint or listening to the last notes of a bell struck far away. Every wave carries information encoded in its shape, and some of those shapes resemble tones, harmonics, structures that we can translate into sound, not because the universe meant it to be heard, but because it behaves in ways that mirror what we call music. In the merging of black holes, the tones rise and fall. There are overtones, there is crescendo, and there is silence. These are not accidents. They are written into the equations of general relativity, into the way gravity curves and bends and restores. Black holes vibrate when they form, sending out a gravitational resonance like the aftermath of a drumbeat. If you could hear it not through air, but through space-time, you would feel it more than listen to it. A slow, deep thrum that shakes the bones of the cosmos. And this music is not rare. The universe is filled with black holes, with neutron stars, with dense, spinning objects crashing into one another. Every collision, every spiral, every ripple adds to the chorus. It is a background hum that stretches across time, a low murmur beneath everything. Some gravitational waves are strong and short, from events we can pinpoint. Others are subtle and long, like the whisper of a million quiet voices overlapping. Even the supermassive black holes at the centers of galaxies are thought to sing. When they merge rare and ancient events, they should produce waves that take years to oscillate once. We have not yet heard those notes directly, but we are listening, with radio telescopes watching pulsars blink across the sky, searching for the tiny irregularities that suggest a wave has passed through. A beat too slow for our ears, but not for our instruments. What we are discovering is that the universe is not just visible, it is audible, in a sense more profound than sound. Light shows us what is, but gravity tells us what moved, what collided, what changed. Through gravitational waves, we are no longer limited to seeing the universe. We can now feel it. This shift is like going from watching lightning to also hearing thunder, a new dimension of experience. And as we refine our instruments and expand our sensitivity, the music will grow clearer. We may hear the echoes of the first stars collapsing, the background vibrations of the early universe still resonating through time. We may discover phenomena we cannot yet imagine, playing notes we do not yet recognize, and so black holes sing, not with voices or instruments, but with gravity, with motion and mass and silence that isn't truly silent. Their songs are fleeting, but not forgotten. They are inscribed in the fabric of space, carried outward on waves that do not fade. And when we listen, truly listen, we begin to hear that the cosmos has always been alive with sound, just waiting for someone to hear it. The shape of the universe is not something we can see by looking out a window or launching a telescope. It is not a shape in the way a stone or a sphere is shaped. It is the shape of space itself, the container of everything, the scaffolding on which all matter and energy are arranged. When we ask if the universe is infinite or finite, we are asking whether there are edges, borders, ends, some ultimate boundary beyond which there is nothing. But here, even the word nothing starts to blur, because if space ends, what lies beyond it? And if it doesn't end, how can it just keep going? This question touches something ancient. From the earliest myths, humans have wondered what holds the stars in place. Is the sky a dome? Is it endless? Are we floating in a bubble of existence surrounded by something else? And now, with satellites and models and physics that bends and twists space itself, we still don't know the answer for certain. One idea suggests that the universe is infinite, that if you could travel forever in any direction, you would never reach a wall or a fence or an edge. Space would continue on, dotted with galaxies like lights on an infinite sea. There would be no center, no circumference, just a vast, unending stretch of space-time, folding and flowing without a border. But even this idea has subtleties. Infinite in what way? Infinite in volume? Infinite in time? Is the fabric of space like a plane, flat and endless, or more like a saddle, curving outward forever? And then there is the possibility that the universe is finite but unbounded. Imagine standing on the surface of Earth. You can walk in any direction and never fall off, never hit an edge, because the surface curves back on itself. The Earth is finite in area, but you can travel endlessly without finding a limit. Some physicists believe the universe could be similar, but in 3 dimensions instead of 2. In such a model, space curves in on itself. If you traveled in a straight line far enough millions or billions of light years, you might eventually return to where you started, having looped around the cosmos without ever realizing it. But space is not static. It's not a rigid container. It expands. That expansion changes how we think about its shape. We know the universe is getting bigger, the galaxies moving farther apart, carried by the stretching of space-time itself. So when we talk about the universe being infinite or finite, we're really talking about a snapshot in time. Space might have been finite when it began, or it might have always been infinite. Its expansion could carry it from one state to another, or preserve whatever topology it started with. To explore these ideas, scientists use the cosmic microwave background, the faint afterglow of the Big Bang. By studying tiny variations in this ancient light, we can infer how space is curved on the largest scales. So far, it appears to be remarkably flat. That suggests the universe might be infinite, or so vast and subtly curved that its curvature is too gentle for us to detect. Like standing on a beach and seeing a horizon that looks straight, even though you are on a sphere. But our instruments have limits. The observable universe, the part we can see, is just a small bubble around us, about 93 billion light-years across. Beyond that, there may be more space, more galaxies, or perhaps something completely different. Maybe the universe loops. Maybe it ends. Maybe it fractures into other universes, each with its own rules. We don't know, and we may never know, because we are confined to this pocket of visibility, like fish in a vast pond who cannot tell if they swim in a lake or an ocean. There are even models in which space is shaped like a dodecahedron or a torus, a kind of 3-dimensional donut. These shapes could cause light to loop around the universe in ways that repeat patterns. If true, we might someday detect echoes in the sky, repeating signals that reveal the topology of space itself. But so far, we've found no conclusive evidence of such loops. And still, the question remains, finite or infinite, a cosmic loop or a sprawling plane, a universe that folds in on itself, or one that reaches forever outward. Each answer raises new questions. If finite, what holds it? If infinite, how did it begin? Where is its center? And how do you define outside when space itself is all there is? In the end, the shape of the universe may be something we carry more easily in math than in intuition. Our minds evolved to grasp hills and rivers, not curved 4-dimensional geometry or abstract manifolds without edges. But even so, we wonder. We build models. We listen to the light left behind at the beginning of time. And as we do, we remind ourselves that not all edges can be touched, not all shapes can be drawn, and not all infinities are the same. The universe may be finite, or it may not be. But whatever its shape, we are inside it, traveling through the curvature of space, building maps with mathematics and dreams, and asking the kinds of questions that only beings made of stardust and wonder would ever think to ask. Far beyond the limits of what we can observe, past the haze of ancient light, and the cold echo of the Big Bang, there may lie regions of the universe that play by different rules, not just different in terms of scenery or structure, but different in the very fabric that holds everything together. The constants we believe are unchanging: the speed of light, the strength of gravity, the charge of the electron, might not be constants at all. The laws of physics, the ones we've come to know so intimately here, may simply be local customs in a much larger and stranger cosmos. We're taught early that physics is absolute, that the rules we uncover on Earth, in laboratories and equations, apply everywhere. They're the universal truths, the code that reality is written in. Drop a ball, bend light, split an atom. The same principles unfold whether you're in a basement on Earth or drifting beside a star in another galaxy. And for the most part, observations support that. From the tiniest particles to the grandest galactic clusters, the same equations seem to describe it all. But what if they don't? What if that consistency is just a local illusion, like the flatness of a plane that hides the curve of the planet? Our observable universe, vast as it is, only stretches about 46 billion light years in every direction. That's the cosmic horizon, the limit of what we can see, because light hasn't had time to reach us from beyond it. And everything we know about physics is rooted in what happens inside that sphere. Beyond it lies darkness, not empty, but unknowable. A silence not of absence, but of distance. There are clues, subtle and unsettling, that hint the rules might vary. Some measurements of the fine structure, constant a number that determines how light and matter interact, have suggested tiny differences in distant parts of the sky. The variations are small, bordering on statistical noise, but they raise a tantalizing question. Could the laws of physics be slightly different elsewhere? And if they are different, what else could change? Imagine a universe where gravity is stronger, stars burn faster, galaxies form tighter, and black holes might be more common and more ravenous. Or a universe where the charge on the electron is larger, distorting the chemistry of life before it even has a chance to begin. If these constants had been just a little off in our own patch of the cosmos, the stars might never have formed, or they might have burned too quickly to host life. Atoms themselves might not have held together. It's easy to think of the universe as inevitable, as if it had to be this way. But when you peel back the layers, you find delicate balances everywhere. Ratios tuned so precisely that a small shift would break everything. And yet, nothing in the laws of physics says these values must be what they are. They simply are. Measured, not derived. Discovered, not predicted. Constants we read from nature's page without ever being told why those numbers were chosen. Some theories suggest there may be many universes not just beyond space, but beyond possibility. A multiverse where each region, each bubble, has its own set of rules. Maybe ours is just one outcome among countless others. A lucky draw from a cosmic deck where other hands played out as chaos or silence. In this view, the laws of physics are local properties of a particular universe, like weather patterns that vary from place to place, or dialects that form when voices are separated long enough. If that's true, then asking why the universe has the rules it does might be like asking why the Pacific Ocean has the waves it does. It's not designed, it's just one instance of something much larger. And that thought, unsettling as it is, carries a kind of freedom, because it means the universe is not a single answer, it's a conversation, a range of possibilities, each with its own rhythm and resonance. But we are bound here, inside this one patch of reality. Our instruments reach only so far. Our theories, elegant as they are, rely on the assumption that the ground beneath us stretches everywhere. We assume that what we see in one corner applies to them all. It's a reasonable assumption. It's served us well. But it's also an assumption built on a tiny sample size, one universe, one version of physics, one narrow lens through which we gaze out at the infinite. Someday, perhaps, we'll find better clues. Subtle fingerprints in the cosmic microwave background, patterns in the clustering of galaxies, maybe even evidence of collisions between universes with different laws, scars left behind in the sky. Or perhaps the truth will remain beyond our reach, forever sealed outside the horizon, a mystery whose very nature is that we cannot touch it. And yet, even that uncertainty is part of the beauty. To know that the rules we rely on might be temporary, regional, flexible. That beneath the order we've mapped out, there might be deeper orders, stranger logics, other ways for reality to unfold. It humbles us. It reminds us that we are not masters of the cosmos, but guests in a universe that still guards its secrets closely. So we continue to ask, to wonder, to listen. And as we do, we hold in our minds two truths: that the laws of physics, as we know them, describe our world with stunning precision, and that they might be just one version of many, written into a sky that is larger and more varied than we will ever fully understand. There is a quiet shift happening in the universe, not the kind that makes headlines or sends out shock waves, but a long, slow exhale, the gentle winding down of creation itself. The stars, once bursting into life across every corner of space, are forming less often now. Galaxies that once blazed with newborn suns are growing dimmer. Gas clouds that fueled stellar birth for billions of years are thinning out, used up, spread too far apart to ignite again. The golden age of star formation is behind us, and what lies ahead is a long twilight. This doesn't mean the sky is empty or still. Not yet. There are still stars being born, still galaxies colliding, still black holes feasting in brilliant silence. But on the cosmic scale, the tempo has slowed. The universe isn't dying, but it is aging. Entropy, the great unraveler, is doing its work, not in a rush, not in a fire, but in a slow fading of structure, a quiet loosening of everything that once burned with urgency. Entropy is often misunderstood. It isn't just disorder or decay. It's the tendency of energy to spread out, to even out, to move from places where it is concentrated to places where it isn't. Over time, it makes stars burn out, galaxies drift apart, and information become harder to retrieve. In the far, far future, if nothing intervenes, entropy will win. Everything will become cold and still, stretched into uniformity. No stars, no heat, no memory. But even now, as that long future begins its slow arrival, the universe is not silent. Because in the cooling ashes of creation, something else is happening. It is remembering. Not in the way we remember names or dreams or songs, but in its own language light. Every star that ever shone sent out light into the darkness, and that light is still traveling. Photons carry with them the imprint of what created them. They remember the temperature of the surface they escaped from. They carry the fingerprint of the elements they passed through. They remember their direction, their energy, their source. Long after the stars that made them are gone, the light goes on. Across the universe, light is a memory machine. It weaves history into space itself. When we look up at the night sky, we are not seeing the present. We are peering into the archive. A gallery of ancient images etched into photons, arriving one after another from different moments in time. Some of the starlight we see now left its source before humans existed, before Earth formed, before even the Milky Way found its shape. It has crossed the vacuum, uninterrupted, to reach your eyes as you lie awake in the dark. And it's not just starlight. The cosmic microwave background, the faint hum left over from the Big Bang, is the oldest light we can see. It is not a glow from stars or galaxies, but from the universe itself when it was still a newborn, just 380,000 years old. That light has traveled for over 13 billion years, stretched and cooled by the expansion of space, but it is still here. It remembers a time when atoms were just beginning to form, when darkness was just starting to give way to transparency. Even as entropy increases, even as stars burn out and galaxies quiet down, this light remains, fading, stretching, scattering, but not forgotten. Each photon is a message in a bottle, a whisper from a moment that will never happen again. And if the universe keeps expanding, if it keeps cooling, eventually the light too will vanish from view, not because it stops existing, but because it redshifts beyond detection, stretched into wavelengths longer than we can measure, lost in the slow widening of space. The memories will still be there, but unreadable. The cosmic photo album, locked shut not by fire, but by time. Yet for now, they are still here, drifting past us, entering telescopes, warming skin, glinting off oceans. Light that carries the trace of something long gone, but not entirely lost. In this way, the universe remembers not just through matter, not just through structure, but through illumination. Light does not forget. It just travels on. And so, when we gaze at the stars, we are not just looking outward, we are looking backward, into the stories of atoms and fire, into the origins of galaxies and the deaths of suns, into the slow, breathtaking unfolding of everything that has ever existed, all of it written in light, traveling still. One day, perhaps, nothing new will be born. Stars will die, black holes will fade, matter will drift into silence. But until that day comes, and it is far beyond any calendar, we know the memories will continue to move through space, not in books, not in minds, but in the form of photons, still racing, still remembering. And here we are, brief and small, but aware, able to read the light, able to wonder, able to ask, in our fleeting moment, what kind of universe we live in and what kind of memory we will leave behind.